So Chris reminded me this morning that it's been almost exactly 2 years since the idea of higher inductive types was first floated at the Wolfach workshop in 2011. So at first, when we first had this idea of defining inductive types by throwing in equalities and paths, we didn't really know what to do with them or how to formalize them or whether they existed. And then that we sort of started to do a little bit more with them. And then that summer, Peter Lumstein and I basically worked out what I'm going to tell you today about how to construct semantics for these things in appropriately well-behaved model categories. And then, of course, since then, we've found that we can do a lot of really useful homotopy theory with them, and that they include lots of important and interesting examples. So I'm going to simplify things a little bit today. I'm going to leave out some parts of the very general notion of higher inductive types, and I'm going to concentrate on semantics. And so in fact, I feel like we understand the semantics rather better than we understand the syntax. So at certain points, I'm going to say, well, this is what we need the syntax to give us, and whatever the syntax is, this is what we have to get out of it for the semantics to work. And in all the examples that we've cared about, we've been able to get this out of the syntax. But it's a tricky problem to specify exactly what the very general syntax should be. Yeah, and I should also warn you at the very beginning that there's going to be a couple of black boxes later on in the talk where I'm going to have to say this is the theorem of Max Kelly or Richard Garner or somebody or other like that, and then we'll sort of take that as a black box and go on from there. But hopefully I'll give you some sort of explanation of where that black box comes from and why we're using it, and it would be a whole other talk to explain it in its own right. So let me just remind you, when I'm describing particular higher inductives, I'm going to use some sort of vaguely Coq-like syntax where you're defining some type, some higher inductive type, and maybe it has some parameters, and maybe it has some indices, and then it defines a type. And then it's defined by giving some constructors, and maybe these constructors in a higher inductive, there are constructors of we call zero constructors, which construct elements of the type itself. So they take some arguments and then they output something in the type, and maybe we have more than one zero constructor. But then we can also have what I'm going to call one constructors, which also take some arguments, but then instead of an element of the type, they output some element in the identity type of U between some points elements U and V, and maybe we can have some other one constructors, and then maybe there's a two constructor in general, which takes some arguments and outputs something in the identity type of of W, B prime, V prime, or something. And then we could go sort of all the way on. And you can imagine being even more general than this, like the definition of n-spheres that Dan Nakata uses in his proof involves an n constructor for variable n. But this is sort of the simple version of the without going on to more complicated stuff like that. And I'm going to simplify it even further by ignoring all constructors of level higher than 1. The ideas that I'm going to describe will work in general for n constructors, but it's just easier to think only about zero constructors and one constructors that contain all the essential ideas. And I'm also going to ignore parameters and indices and just sort of work with an ordinary inductive types rather than inductive families.
Why did you write the line zero constructor twice? I'm sure you said it, but I missed it.
Because there might be more than one of them. I mean, I should probably have just put a ... or something. And another thing which is going to become clear as we go along or towards the end is that with the constructors don't really have to come in order of dimension. So I've written them in order of dimension like this. But we could have a zero constructor and then a two constructor and then a one constructor and then a zero constructor. And so we could write them we could choose to write them in any order. But the order that we write them in does in fact matter, but it doesn't have to be the dimension order. And the reason the order matters is that the constructors, the type of one constructor could refer to the previous constructors in you could make different choices about that, and I'll say something about that more later on. Okay. So that's what we can say about the. That's what all I'm going to say about the syntax for the moment. And now over here, I want to say something about what the semantics looks like that we're going to look at. So I'm going to work in. Well, I want to say I'm going to work in, but actually, everything that I say is going to make sense in the context of a model category which has a bunch of very nice properties. So I'm going to just write these down and then not explain them. It's locally Cartesian closed, right proper. The cofibrations are the monomorphisms. It's locally presentable as a category. It's cofibrantly generated, which means that there's a small collection of cofibrations and trivial cofibrations which generate the whole thing, and it's simplicial. So roughly, these three conditions mean that we can model type theory. These two conditions mean that we can do transfinite composition arguments, and this condition means that we have sort of well-behaved simplicial homotopies. But if you don't like these conditions, then you should think about simplicial sets. So simplicial sets has all these properties, and in some sense, this is the simplest model in the case that we probably care the most about. Yes. Exactly. Yes.
So monads are
All monos are also cofibrations. Yeah. Yeah. So that's sort of the OR example, but also it's true that any infinity topos admits some small model category presentation with all these properties. So Denis Charles Sasinski proved this, and then Joachim and David Gebner also gave a different proof. All right. So let me also remind you briefly how the interpretation of type theory works in a context like this. So types in type theory correspond to fibrant objects. So a fibrant object is in simplicial sets, this is a Kahn complex. A family of types in some context is represented by a Kahn fibration, or a fibration in the model category. The equality type, the identity type between two objects, two elements of a type is represented by the path object fibration. And I'm going to, because we're in a simplicial model category, I can use a particular path object, which is just the mapping space out of the simplicial unit interval. And I'm also going to need, we're also going to need the notion of dependent path. So there can be some notion in type theory if I have a family of types over a type A, and I have two elements of A and a path between them, so x equals y, and I also have something over x in my fibration and something over y in my fibration, then I have a notion of path over p from u to v. So I'm sort of interchangeably using id and equals for the identity type. They're the same thing. So there are different ways to define this. The easiest way is to define this.
Can you slow down a little?
Yeah.
So you consider there to be some sort of a type of dependent path?
Yeah, type of dependent paths. So this should be regarded as a path from u to v in the total space of this fibration lying over this path from x to y.
Yeah, but do we actually have it?
Well, one way you can define it is as the path from the transport of u along p to v in the fiber over y. You could also define it as a transport, a path from U to the transport back along P of V. You can also define it directly as an inductive type in its own right, using it to take the notion of some sort of heterogeneous equality between these two types.
Between these two terms.
Yeah, sorry, between these two terms. Living in these different types that are parameterized by this family.
But I mean, can you do it in Coq? Like
Yeah, you can define it like that.
Yes.
Why don't you just write down one of the definitions?
You can only do it like that.
What?
In Coq, you can only do it like that, but there is another way.
No, there's another way. Let's see.
What you've written there in pink or whatever
Yeah,
is a perfectly good.
it's a perfectly good definition. Yeah.
Okay, but like, put your right hand horizontal.
Yeah, sure. Let's see if I can. Let's see. So we want to say so we have A and B, and X, Y are in A, and P is from X to Y, and then we're something like BX to. Well, no, actually, I want. These have to be all indices too. So X and Y are in A, P from X to Y, BX, BY to type. And then I have a constructor which says given X in A and U in BX, whatever this thing is, indexed paths. I have an indexed path from over X, X, and the referral of X, and from U to U. So I have a reflexivity generator which lives over reflexivity, and then that defines this whole inductive family.
I think you proved that that's equivalent to
Yeah, you can prove that this is equivalent to that. And it's important that I don't really care what the definition is. I could take any of these definitions and they're all equivalent to each other. And in the semantics, what I want to use as the definition of this thing is the mapping space into the total space of this vibration B. So this I have a map from this thing. So this thing is functorial. This construction of path objects is functorial. So I get a map from this whole thing to this whole vibration. And if I take the pullback of these projections, then I end up with a vibration from the path space of the total object B into this pullback, just by properties of being a simplicial model category. That's sort of black box that. And the point is that this pullback it represents this whole context over here. Right? So we have X and Y in A, and P from X to Y, and U over X and V over Y, and those all go into this context. And then this vibration here represents this dependent type over that. So whatever we might choose, it's going to be equivalent to this one, and so I'm going to use this one as my meaning of this.
Well, okay, so since you don't actually describe any sort of eliminators for this type, then you can choose whatever you want until you.
Well, it has the eliminator that this thing does.
Mm-hmm.
All of these definitions have the same eliminator that this thing does.
Okay.
And so does this one. But sort of, I mean, the fact that these are all only equivalent to each other is what gives the computation rules for path constructors are going to be only propositional. So that should become clearer later on. But sort of depending on what choice you make for this definition, then the computation rule for path constructors might have to pass along some equivalence in the semantics between this thing and whatever your choice was.
Presumably also have some problems with the exact computation between eliminator and pullback.
No, you can get that, I think, automatically from just using a universe in the usual way that you came up with.
Well,
Yeah.
but there is a fit there which is not over. Okay, let's talk about it later.
All right.
But Mike, isn't this heterogeneous equality just a convenience? You could proceed without it, right? You don't need
Well-
it for what you're going to do.
Well, you need some notion of heterogeneous equality in order to
Let's not call it
state the
heterogeneous equality,
whatever it
it's
is.
not heterogeneous equality.
Well, it's an equality between two things that live in different types, so it's heterogeneous in that sense. Yeah. dependent equality or
Dependent
indexed
equality.
equality.
Dependent equality.
Yeah.
Dependent equality. Heterogeneous is when people take two types which are totally unrelated to each other and decide to compare their objects.
You need something of this sort in order to state the eliminator for a higher inductive type.
Yeah, of the pink sort there, would suffice.
The pink sort would suffice. My point is that in the semantics, I want to use this.
I agree that it's more convenient to use. I'm just saying it's not essential for the theory of higher inductive types to introduce this dependent equality relation. You could do the whole thing. And in fact, we have in the past in type theory without it.
Yeah, but by defining it to be this, by taking
Yes,
this, yeah,
exactly.
yeah, that's right. Yeah, but
So if anyone feels uncomfortable with that,
Yeah.
well-defined notion, nothing that you're going to do actually depends on that.
no. Yeah, I mean, you're perfectly free to consider this as notation for this. The point is that just that in the syntax, in the semantics, this is only equivalent to this, rather than I'm more Victor. Okay. So I didn't seem to leave myself very much room, but the one other thing which I wanted to mention in terms of what this semantics gives us, so the fact that we're using these cotensor path objects maps out of mapping spaces out of the simplicial interval means that we have two adjoint characterizations of homotopies. So if I have in the context, if I have sort of a homotopy between two functions f and g in type theory that looks like this, then in the semantics that looks exactly, if I interpret things literally, that means a map from H from A into the path space of B, which lies over FG, mapping into B cross B. Because this is sort of the dependent type, and I'm considering a section of that dependent type over F and G. But mapping spaces out of the simplicial interval have an adjoint to products with the unit interval. So I can equally consider this to be a map from A cross the interval into B. And then the fact that it's a homotopy from F to G means that if I restrict it to A plus A, the coproduct, along the two conclusions, I get F and G, respectively. So I have these two adjoint characterizations of homotopies, and that's going to be important when we're building in these homotopies to the higher inductive types. Okay? All right. So the overall picture of trying to connect this side of the blackboard to this side of the blackboard is that there are a bunch of obstacles which form a three-simplex. So one obstacle is coherence, which Vladimir also already mentioned. Another obstacle is vibrancy. And then we have higher paths, so which is sort of the essential ingredient in having higher inductive types rather than ordinary inductive types, and recursion. So what I'm going to do is I'm going to discuss each of these obstacles individually, ignoring the other three, and then I'm going to try to put them together in pairs and triples and eventually build up to the whole three-simplex where we can deal with all of them at once. Okay? What was that? So the overall picture for how we build semantics, or so how we build the eliminators, is in the semantics we have some notion of algebra, and the inductive type, the higher inductive type, is supposed to be some sort of initial algebra or homotopy initial algebra, but the eliminator property that we're looking for doesn't express that directly. It expresses it by some sort of dependent elimination property. So what that means is that fibrations of a certain sort have sections. So whatever the syntax is, we're going to build from the syntax a notion of algebra. So a type is an algebra if it has some particular structure, and then there's a notion of algebra map, which preserves that structure in some sense. And then the dependent eliminator says, or the elimination, the property of an inductive or higher inductive type says that W is an algebra, so it has whatever structure we're talking about, which is represented, which basically sort of encapsulates what all the constructors are supposed to be. And then the elimination, the real part of the elimination property says that if I have any algebra fibration over W, there exists an algebra section. So given W is an algebra, so given any fibration over W, which is, so this is a fibration, and it's an algebra map. So in particular, that means that P is an algebra, and this preserves the structure. Then we conclude that there exists an algebra map, an algebra section. An algebra map, which is a section, this composite is the identity of W.
I thought it was the constructors that tell you that W is an algebra.
Yeah, the constructors are what tell you that W is an algebra. So, okay, so this is not, yeah, I shouldn't have called this the eliminator.
It's not exists a section, it's given a section.
Yeah, yeah, exists in the type theoretic sense. Then
But exists in type theoretic sense, it's a member of the squash type.
no, I'm using, I mean, in propositions as types, exists means sigma. And if I wanted to squash it, I would put an adverb on it. An adverb on it, I would say that merely exists.
Merely exists.
Yeah. Okay. I don't want to get into this, so I will say a specified.
Given is a good word. It's short and clear.
A specified algebra section.
So wherever it is given a section.
Okay. So this, I just sort of wanted to remind anybody who doesn't know that this is sort of a nice way of expressing what it means to be a homotopy initial algebra without having to talk about equality of maps other than like sections of dependent types. So if W is actually a strictly initial algebra for, then because P is an algebra, there exists a map here, which is an algebra map and a unique one. And moreover, this composite is an algebra map from W to itself. And so if W is actually strictly initial, it must be the identity. So any strictly initial algebra does in fact have this property. And conversely, if W has this property, then we can use this thing to build some sort of homotopy initiality of W. So Steve and Christina and who else? Somebody else, I forget. What? Nicola proved that that's true for ordinary inductive types, and people have done it in particular special cases for some higher inductives as well. The basic idea is that so W has an algebra map to everything else by the eliminator, and if you have two maps and you want to show that they're the same, then you take their homotopy equalizer, or essentially what you do is you take in homotopy theory, you take the path object and you pull it back along the map, say FG, and then this is an algebra map, and so fibration, and so it has an algebra section, which gives you a homotopy between F and G. And so that tells you they're unique up to homotopy, and then you can boost that up to having a whole contractible space of algebra maps. So I don't want to get into that very much. I just wanted to mention that, so because this is the elimination property that we want to get out for our algebras. Okay. So let's.
It's equivalent to saying it's homotopy initial.
It is, but that's sort of a non-trivial theorem, that it's equivalent to being homotopy initial. And I don't know if, since we don't have a general definition of higher inductive type, nobody's actually proven it in that case.
Whereas this is obviously equivalent to the dependent elimination.
Right. So if you just take the dependent elimination rule written in type theory and you unravel it in terms of the syntax that I wrote over there, this is what you get. Modulo some coherence, which is the fourth obstacle that I'm not mentioning yet. Yeah.
Definition of a algebra fibration over W is a fibration, the total space of which is an algebra, or it's a fibration of algebras?
It's a fibration of which the total space is an algebra, and the fibration itself is an algebra map.
And the
Yeah. I'm about to do some examples that will hopefully make that a little bit clearer. Okay. So.
Maybe the naive example is natural number.
Yeah. Yeah. Okay. Okay. We do the natural numbers now if you want. You want to see the natural numbers? So, so for the natural numbers, an algebra is a type X together with a map from 1 to X and a map from X to X. And an algebra map is a map which preserves these structure. And so an algebra fibration over the natural numbers is a fibration together with a map from 1 into P which lives over 0. So an element of P of 0, the fiber over 0, and then a map from P to itself living over the successor. So that's essentially a map from the fiber over n to the fiber over the successor of n.
Is this square commuting strictly?
Strictly.
You want it to commute strictly?
Strictly.
But you could also.
You could ask for it to commute up to homotopy. But if you look at the actual eliminator in type theory, what you get out is that it commutes strictly. So the induction rule is that if I have sort of a d0 that lives in P of 0, and I have ds that says for all n, P of n goes to P of the successor of n, and then I conclude for all n, P of n. So this commutes strictly because d0 is actually in the fiber over 0, rather than in some other fiber that's homotopic to it. And this square commutes strictly because this maps the fiber over n literally to the fiber over Sn, rather than some fiber homotopic to it. So normally we can't say in type theory that squares commute strictly, but if there's a fibration on one side, then we can by specifying what the index is of this as a dependent type.
Yeah.
Okay? So let's suppose, to start off with, that we have no obstacles at all. So we're going to pretend that all types are fibrant, that all objects are fibrant. We're going to ignore recursion. So ignoring recursion means that these arguments cannot involve W. Right? So that's what recursion means, is that these constructors can take things from W itself. So these arguments are just types, just sort of fixed types that have nothing to do with W. And we're going to ignore higher paths, so that means we have only 0 constructors. So it's an ordinary inductive type, not a higher inductive type, and we're going to forget about coherence. So the only sort of example that is of any interest here is a coproduct. So for instance, some coproduct of A and B has 2 constructors, one coming from A and one coming from B. In this case, what it means to be an algebra is that we just have those functions. So A and B are fixed objects in our category. They're interpreted by fibrant or by objects. And so an algebra is going to be an object X together with a map from A and a map from B. And then an algebra map is going to be a map which preserves those maps from A and B. Okay, so what is the initial algebra? An initial algebra is a coproduct of A and B. Right? That's just basically the definition of a coproduct. So that's the easy case of no obstacles. Now let's add in. Let's say something about coherence first of all, in the case of no obstacles. So coherence in this case means that these specified algebra sections have to be preserved by reindexing and by substitution. So what this means is that basically, first of all, for any context gamma, we have to be able to put W in that context, and then whenever we have an algebra section, this is coherence, whenever we have an algebra fibration over gamma times W, so this is some sort of indexed algebra fibration, then there's a specified algebra section. So in this case, we get that because gamma times the coproduct is a coproduct.
Michael, you
Yeah.
also want this to be to commute with pullback
Yeah.
from gamma prime to gamma.
Yeah, this is the first part of coherence.
Oh, sorry.
So the first part of coherence is that in any context we get this elimination, right? And so this essentially says that the universal property of W is preserved by pullback from the empty context to gamma. So I'm being a little bit imprecise about what I mean by an algebra fibration over here. So this whole thing basically takes place in things over gamma. So this has to be an algebra over gamma, and this is an algebra over gamma, and this is an algebra map over gamma.
So it's the same as before, except that it's in
It's,
context gamma.
it's in the slice category over gamma. It's in the context gamma.
And you want these sections to be coherent.
Right. You want these sections to be coherent. So what I said here is that these sections exist in this case because when we pull back a coproduct to gamma, we again have a coproduct. So it again has the right universal property. So that's the first part of coherence. And the second part of coherence is that if I have a map from gamma prime to gamma, then pullback preserves these sections. So this has to do with preserving in the sense of judgmental equality in the type theory, which is literal on-the-nose equality in the category. And the reason that this has to happen is because because pullback along maps of context is substitution of variables, and so if I have the recursor is given by a term, and so I just substitute the values of some variables in that term, and it's again an instance of the same term, so it has to be the same elimination.
From I don't know, a philosophical viewpoint or moral viewpoint, I don't know. It's because this thing is actually unique up to contractible. The sections are unique. Contractibly unique.
Contractibly unique is not enough to get this property.
No. So
But
being contractibly unique is the sort of the basis on which you can say, well, let's make it truly unique.
you might say that, I guess. Yeah, it's not unique. It's just specified.
Yeah, I understand.
Yeah.
I understand. But by specifying it, you're making it unique.
Unique with the property that it is the specified one.
Okay.
Okay. And in this case of no obstacles, this is automatic because it is literally unique, right? So because we have a strictly initial algebra, there's a unique map from A plus B into whatever, and so as we pull it back, it's still such a map, and therefore it must be equal to the specified one. Okay, so that's the case of no obstacles and coherence. Now let's talk about vibrancy. So if we start with the case of no obstacles, we add vibrancy. The problem now is that this initial algebra property gives us a coproduct, but the coproduct might not be fibrant, even if A and B are. It's true in the case of simplicial sets, but that's sort of an accidental property of simplicial sets, and it's not going to be true in general. So if you'd like an example, so take consider the category of simplicial presheaves. is a model for some infinity topos, and you have a model structure in which the fibrant objects are the higher stacks, the higher sheaves of some sort, then the coproduct of sheaves is not, as pre-sheaves, is not in general a sheaf anymore. You have to sheafify it because you might have sort of collapsings that you need to put in, and then you have to glue things together to get the real coproduct of sheaves.
So you may have to have like vibrant coproduct and the usual coproduct.
Right. Yeah. So basically what we need to do is we need to take a fibrant replacement of the coproduct. Right? The fibrant replacement in these cases is the sheafification. Okay.
Doesn't happen at this point. Yeah. Jen is looking at it.
Okay. So here's our coproduct A plus B, which is not necessarily fibrant, but we have a fibrant replacement of it. So one of the things about a model category is that, right, I can factor any map into a trivial cofibration followed by a fibration. So if I do that to the map from A plus B to the terminal object, then I get a trivial cofibration into a fibrant object. And this fibrant object is usually written as R of something for reasons which are kind of obscure. So my claim is that this R of A plus B has the correct elimination property to be the coproduct in the type theory. So it is fibrant because we've constructed it to be a fibrant replacement. So what we need to know is that if I have it, and it is an algebra, right? So to be an algebra, it has to have a map from A and a map from B. But it has a map from A and a map from B. They just come through A plus B, mapping into it. And so what I need to know is if I have an algebra fibration over it, then it has an algebra section. So this is an algebra fibration. That means that I have a map from A into P and a map from B into P, which live over these maps. And that, right, the universal property of the coproduct gives me a map from A plus B into P that commutes with all of these things. So I have this commutative triangle. And now if I reorganize this commutative triangle as a commutative square, then I can use the lifting property in a model category. So if I write it as A plus B maps by a trivial cofibration into R of A plus B, and then this is the identity down here to R of A plus B. Here's my fibration into P. And then because I have a fibration over here and a trivial cofibration over here, I have a diagonal lift. So the fact that this triangle commutes says that it's a section of the fibration. And the fact that this triangle commutes says that it's an algebra map, that it preserves the maps from A and B, the algebra structure. Okay, so in the simple case of no obstacles, just taking the fibrant replacement gives us something which works.
We have to select that section.
Right. So now, if we want to add coherence, then we have more of a problem, right? Because there has to be a specified section. So we have to pick such a section when we're building the model to call it the eliminator. And so now we need to know that it's going to be coherent in these ways if we want to put together vibrancy and coherence. So this is the point where I'm worried that Vladimir is going to attack me.
I'm planning a later meeting to discuss
Yeah.
in more detail.
All right. So vibrancy plus coherence. So we need to know that if I pull back this thing to gamma, then it still has this property. And then we need to know that these lifts can be chosen in some coherent way, which is preserved by pullback. So it's not in general true that pullback, this is no longer a coproduct, so I can't use the fact that product or pullback preserves coproducts. But it is true under all my hypotheses of my model category that pullback to a fibrant object gamma preserves the trivial cofibrations. So a trivial cofibration is precisely a cofibration which is a weak equivalence, and a cofibration is precisely a monomorphism by assumption. And monomorphisms are always preserved by pullback. And weak equivalences are preserved by pullback along a fibration in a right proper model category. So that means that pullback along a fibration preserves trivial cofibrations. In particular, pullback along the fibration from gamma to the terminal object preserves trivial cofibrations. So that means that the map from gamma times a plus b, or sorry, a plus b, into gamma times r of a plus b is again a trivial cofibration. And now if I have an algebra fibration over gamma times r of a plus b, then I get a section like this, and now I can again use the lifting property to get a section over gamma times r of a plus b. Trivial cofibration. Acyclic cofibration is the other word for it. So this is part one of coherence.
Maybe just a remark.
Yeah.
Gamma is fibrant.
Gamma is fibrant because all types are fibrant objects, and gamma is a context, so it's built up out of types. So gamma comes with a tower of fibrations leading down to the terminal object, so it's fibrant. Yeah? So, sorry.
The projection to RAB is a fibration too.
This? Or?
Maybe you don't need to invoke the right properness to get that because gamma is fibrant.
So if I don't have right properness, then pullback of a weak equivalence between fibrant objects is a pullback. It is preserved under, but a plus b is not necessarily fibrant. So this weak equivalence from this non-fibrant object to this fibrant object, I don't think it might not be preserved.
You're right.
Steve, did you have a question or comment?
I'm worried that we're showing that the construction of the coproduct here is stable, and the construction was given in terms of fibrant replacement. Now, when you made the pullback, you pulled back the fibrant replacement, but it seems what you really need to do is take the fibrant replacement after the pullback and compare that with the results of pulling back the fibrant replacement. So you need to pull back A and B over gamma, take their coproduct over gamma, and then take the fibrant replacement to get the corresponding construction.
So I think maybe you are thinking about a different kind of coherence than I'm thinking about right now. So I'm not allowing A and B to be parameters. So A and B are just fixed types at the moment. So I'm not saying that if I change A and B by pulling them back, then I should get the same coproduct as the pullback of their instructions.
Not A, B are not allowed to depend from gamma themselves.
Right, right.
Start with, so, yeah.
Yeah,
So that's right. There is an extra layer of
yeah, which I'm ignoring. So at the moment, A and B are just fixed types in the empty context, and I'm defining some AB as A plus B as a coproduct, as a type, inductive type all by itself.
They look like parameters there.
Yeah, I shouldn't have put spaces in there. So this is a single type, some AB, which I'm defining.
Not that I object to having fibrant replacement commuted with pullbacks.
Well, yeah, so fibrant replacement commuted with pullbacks is a little bit subtle.
Not out of the question.
Yeah. Okay. Other questions, comments? All right. So for now, what we need to know is we need to know that these lifts are themselves preserved by pullback. So that if I do this over gamma and I get this lift, and then I pull it back to gamma prime, and I do the same thing, and I pull back this lift to gamma prime, then I get the same lift that I had chosen over gamma prime. And so the way that we do this is the same way that Vladimir found to make all the structure of type theory coherent is by doing it once over the universe. So we let gamma, I don't know, maybe I'll call this gamma W or something, but this is a particular context, gamma. This is the universal eliminator context. So whatever that this is a context which consists of an algebra fibration over W, right? So this is a context like P is a dependent type over W, and I have a map from I have like for all A in A, I have something in P of in left of A, and then for all B, I have something in P of in right of B. So this context here, sort of an element of this context is essentially an algebra fibration over W. And so whenever I have some other context and I have an algebra fibration over W pulled back to that context, that's classified by a map into this context.
When are you talking about W or 7?
Okay, W is my general inductive type.
In this case, you have A and B that appears.
Yeah. So in this case, W is A plus B. Yeah. Yeah. But for whatever general W isn't, so I guess since I said these, I should really have written some AB. Thanks. So whenever I have some other context with an algebra fibration over the sum, over the coproduct type, then it's classified by some map into this type, into this context. So if I know that this context is fibrant, and so I can do this thing over here for this particular context and choose a lift. And then I define the lift in the other context by pulling back that lift that I chose here along the classifying map of that structure, right? And then it's
That's probably where I'm going to conflate. Because I think you're talking away something which is more complicated than you're making it look.
I don't want to get bogged down in this, but can you?
That's the
Yeah.
only place which I
Okay.
think we should then meet it and discuss it.
Okay. Would you like to say anything very briefly for other people about what you're worried about?
I don't know if I can say it. I'm trying to find a good way of saying it.
Maybe we should just talk about it later.
Let's talk about it later.
Okay.
Because I'm not sure. I haven't thought about this particular example of disjoint union of coproduct.
Mm-hmm.
I thought about this in the context of identity type as an inductive definition.
Mm-hmm.
And there I know that one has to do some non-trivial manipulations with things. And at the end it all works. But it's just the explanation is slightly more complicated. But okay, let's talk about it later and then we can...
All right.
You and Peter have this written up, what you're
Sort of. We have something of a note which we circulated privately to a few people, and I'm probably post on the wiki after this talk or something, so people can have a look at it. It's a little bit hard to read because it's written in greater generality and is not really explained in the building up gradually way that I'm trying to do right now. So at this point, I'm going to hope that you will allow me to postpone coherence to the discussion with Vladimir later on and ignore that coherence obstacle completely. So whatever works with coherence here, trust me that it'll work with the more general stuff that I'm going to talk about. Okay. So now what's left is higher paths and recursion. Okay. So now we finally get to the higher part of higher inductive types.
And parameters and indices.
I'm not going to do those. They're crossed out in green. They'll not appear today. Yeah. So here the example that everybody wants to see is the circle. Right, so we have base, which is an element of the circle, and then we have loop, which is a path in the circle from base to base. Okay, so putting this into the framework of algebras and algebra fibrations and algebra sections, what should an algebra be for the circle? So we just look at what this structure gives us in the category theory. So we have a type X, and then we have a map b from 1 to x, which is the base point, an element of x, and then we have a path from that thing to itself. So this is a homotopy, so a map from 1 into x, this path space of x, which lies over b comma b. Okay, so this is what it means to be an algebra for in this case, and if we think about what it means to be an algebra fibration, then that is what gives how we extract the eliminator for the circle. So whatever the circle is, it's going to have the property. So let me describe the circle eliminator. So S1 is going to be some fibred object with the elimination property for these algebras. So if I have any fibration over S1 with the property that, first of all, I have a point of P living over the base point, and then I have a point of, I have a homotopy here living over the loop. Right, so this loop lives over the loop. Then I'll have a section of this fibration. So, and if we look at this square here, is this square which I left up here. Right? So, if we write out the eliminator in type theory, what's going to happen? L is going to have to be one of these indexed paths. What did we call them? Dependent paths lying over the loop. So that's how the eliminator for the circle that you might have seen comes out of this. And if we write it like this, we usually write it like this when we do it in type theory. So I have some space living over the circle. I've drawn a torus. And now to give a section of this map is to give a point in the fiber over the base point together with a path which goes around this space. Maybe it loops around the back, it does some funny stuff, and then it comes back to the same point. But it lies over the circle in this fibration.
And what this says that to give such a path is enough to actually produce the loop at the base point at P.
So this says that to give a section of this fibration, to give a map from the circle to P, it's enough to give the base point and the path. So from a topological point of view, it sounds kind of tautologous.
Defining the circle.
Right.
Using that property.
Right.
Circle is the thing that
I thought that you would say provide the loop in the path in the fiber of P.
Well, if you translate it along this here,
okay.
right?
Okay, you could do that.
Yeah. So this path over here could equivalently be regarded as saying, take this point, transport it along the loop, and now find a path from this point to this point. So I could take the one which goes around the back in this fiber. So those two kinds of paths are not literally the same, but they're equivalent. And so the semantics is giving us this most naturally, because we're just talking about this map being an algebra fibration, so it respects these path-based objects. And then we can make it equivalent to this, and we'll get a propositional eliminator. Yeah.
Introduce the type into the rules, and it would be a definitional.
Yeah, I mean, you can make it a definitional eliminator if you want. You have something called the dependent paths. Yeah.
You don't want to come back on this topic, but you said you could define it as a dependent path type, but you can also define it as this simple path type using transport in the middle.
Yeah.
You consider that the two are equivalent.
Yeah.
Somehow get some more
Yeah. I mean, I feel like the notion of higher inductive types is most naturally formulated in terms of a notion of dependent path. And especially if you go on higher up, right? The expressing of the higher paths in terms of transport gets more and more fiddly. But it's useful to be able to define them equivalently in terms of transport as well. Sorry? Yeah, it looks more symmetric this way. Okay, so how do we build such a circle, such a type with that property? Well, we can use this fact, which I raised a while ago, about how homotopies have an adjoint characterization in simplicial sets or simplicial model category. Right? So this picture here can equivalently be written by saying that I have a map from P plus P into P, which factors through P times the interval. No, sorry, 1 plus 1. Okay, so here's base comma base, and then B comma B up here. And then the loop can equivalently be regarded as a map from the simplicial interval into the circle or into the thing over that which lives over that. Okay? So that means that I can build the circle. If I ignore the vibrancy issues, I can build the circle using a colimit in the model category in the same way, because everything is now everything is about maps into the circle, maps into the circle, maps into P, in the same way that we took the coproduct, right? So here I can define so being an algebra. So being an algebra. X being an algebra is the same as saying I have a map B from 1 into X, and then I have a map from the simplicial interval into X with the property that when I restrict it to the two endpoints, 1 plus 1, I get B comma B. So I'm factoring through the fold map from 1 plus 1 to 1 into B. So having a commutative diagram like this is the same as saying that X is an algebra of this sort. But that means that it's exactly the same as having a map from this push out into X. So whatever this push out is, it's the initial algebra. Okay? I'm only doing higher paths here. I haven't put in vibrancy yet. So we're pretending that everything is vibrant. So in simplicial sets, this push out is the sort of the very concrete circle that you might build. It has one zero simplex, and it has one non-degenerate one simplex from that one to itself, and then everything above that is degenerate. Everything else is degenerate. You identify the two endpoints of the one simplex. Okay, so since it's the strictly initial algebra, it will have the elimination property sort of on the nose for the same reasons that the ordinary coproduct did. Okay. So now we can add vibrancy to that. So here's our initial algebra H, which may not be vibrant, and in fact, in simplicial sets, even it is not vibrant. And then we can take a vibrant replacement of it, RH. We have a trivial cofibration, and RH is an algebra because it has a map from H. So if I have an algebra vibration over it, I get, since P is an algebra, I get a map from H into here, and now I have my lifting property, which gives me a section in the same way that I had over there. So the vibrant replacement of H, whatever that is, has the elimination property of the circle, and it is vibrant. So it actually represents the circle type in the semantics of the type theory. Now, it doesn't matter, I should mention, right, it doesn't, so far it hasn't really mattered what fibrant replacement we use. There are lots of different ways to fibrantly replace a simplicial set or an object of some other model category, and they're all homotopy equivalent, and this argument shows that in fact they all also have this elimination property, which is a little bit stronger than characterizing them up to homotopy equivalence. Okay?
Yeah. And in this case, I guess the simplicial sets, you don't get vibrancy automatically.
Yeah, this H is not fibrant in simplicial sets.
So
You need something else, yeah. And whatever, and in this case, RH is going to be infinite in particular because you need to throw in all the composites of that generating loop. So we'll have infinitely many one simplices,
So
yeah.
for simplicial set, can one describe LH as being we add in a free way the filling?
RH, yes. So I'm going to come back to this later on, but so that there is sort of an algebraic way to freely add fill-ins. You can either sort of add them freely in some sort of strict way or just sort of freely up to homotopy and sort of keep throwing them in and forget whether you've thrown them in already, and eventually you've thrown in enough and you're done, which is sort of the traditional homotopy theorist way to do it. But there are also more controlled ways to do it. One of them is this sort of this x infinity functor, which is a sort of more or less concrete construction, and so lots of different ways to do it.
Are the initial algebras, I mean, as long as you're, even the recursion we haven't done yet, but are they automatically fibrant in simplicial?
So you mean if you only have zero constructors? Maybe Vladimir can answer that. If I only have zero constructors, it's sort of like just a W type with maybe combined with some coproducts.
Where the arguments of the constructors are fibrant.
Sure, but they're types, so they're going to be fibrant.
Okay, if
Yeah.
yeah.
Yeah, and if you have no indices.
Right, and you don't have indices, then it's all right.
Yeah.
Then you get parameterized container, and the initial algebra from the corresponding functor. The functor will be kind of pulling back, pushing down, and setting composition. And that takes fibrant objects to fibrant objects. And since the initial algebra is just a very long colimit of iterated function, and colimits preserve fibrancy, then you get a fibrant object.
Which is another accidental fact about simplicial sets that, that sequential colimits preserve vibrancy. That's also not true in general. Okay, not doing too badly. Okay, recursion. So now we're going to finally allow the arguments to depend on W. Okay, so we're not doing. We're going to leave off the higher paths for now, and we're going to leave off the vibrancy, and just think about recursion. So we can think about a type like the natural numbers, which I already wrote up before, right? So natural numbers have 0, which is a natural number, and successor, which maps from the natural numbers to the natural numbers. And then an algebra is an object together with a map from 1 and an endomorphism of that object. Right. So, and then that gives us the proof by induction principle for natural numbers. So more generally, what happens is we have a bunch of zero constructors, and each zero constructor gives us an endofunctor. So each args, whatever that args is in the definition of an inductive type, leads to an endofunctor of the category f or f sub s or f sub whatever the arguments are. In general, usually the syntax restriction on these arguments makes this endofunctor well behaved. So I'm not going to get into what that syntax is, but whatever it is, it implies that this functor is accessible.
What category?
Our model category, simplicial sets or whatever model category is. So, for example, in the natural numbers, what are the arguments in this case? So the arguments in the case of 0 is just constant at the terminal object. So because this constructor has no arguments, it just sort of gives you an element. The there's nothing we need to put into the arguments here. And the arguments for the successor are the identity functor. So fs of x equals x. And so what happens is that the algebra structure is going to be given by maps from all these f of x's into x itself. So an algebra is x together with maps from f of x into x for all constructors. So in the case of the natural numbers, we have a map from 1 into x, and then we have a map from x into x, which was what we said was the notion of algebra before.
So f is f naught plus f.
Well, OK. So actually what I wanted to say here is we have a map from f sub I of x into x for all constructors I.
You don't want to sum them up.
Not at the moment. So it could be that, right, so a map from f sub I of x to x is the same as a map from the sum of all the f sub i's into x. But this way of thinking about it is going to be better when we go to higher paths. All right. So what we want to be able to build is we want to be able to build an initial algebra of this sort. So we want to make initial algebras for endofunctors, or initial algebras for families of endofunctors. So we can actually do a little bit better than that. So if I have an endofunctor f, then I have the category of f algebras. So this is objects x together with a map from f of x to x.
So f sort of sends the context to the augmented context given by the argument?
No, f sends a type x to what you would get by substituting x in for w in the expression for the arguments.
In your example, they are polynomial functors.
Yeah, so the usual restriction on whatever occurs in args makes these into polynomial functors.
Strict positivity.
Yeah, strict positivity. But for the semantics, what matters is that they're accessible. They preserve sufficiently highly filtered colimits, which is true of all polynomial functors. OK?
You don't need to preserve fullbacks.
No, I don't think we need that. We will, at some point, we do need to assume that they preserve fibrations landing somewhere or other. But I think that's at a point that I'm not going to get into in this talk. So we have the category of f algebras, which has a forgetful functor down to our model category, simplicial sets or whatever the model category is. And in fact, this functor has a left adjoint. So I'm going to call this left adjoint f bar. And so in particular, f bar of the initial object of C is an initial f algebra. And the way we construct this left adjoint is with this infinite composition that Vladimir already mentioned. And so I start from x, and then I take x plus f of x, and then I take f of what I had before, x plus f of x, and I add x to it again. And then I do that. I continue doing that, and I take the colimit, and then that colimit is my initial algebra. Well, sorry, the colimit is the free algebra on x. So
Well, I kind of do it again for the colimit. For the colimit, you again add x and apply f, and so you do it.
you need to do it long enough so that f preserves the colimit.
Yeah, so you do it
Yeah.
transplant it.
Yeah. So if f preserves countable sequential colimits, then I can stop after omega steps. And in general, I need to go on long enough that f preserves the colimit. If you haven't seen this before, it's a nice exercise to prove that this does in fact give you the free algebra on x, the left adjoint to that. You can just sort of sit down and calculate it. OK? So that gives us an initial algebra. And then that gives us something which satisfies the elimination property for something with a single constructor. And if we had multiple constructors, then we could do this thing that Steve mentioned by taking a coproduct of these endofunctors pointwise to get another endofunctor and then build the initial thing on that.
I know the usual construction of initial algebras where you just start with 0 and then iterate f. But this is sort of a parametric version.
So if I took x to be 0, the initial algebra, then adding x does nothing. And so this will be exactly what you just said. Yeah.
But here you do a more general
Yeah,
construction.
right. Yeah, so I'm building the whole left adjoint rather than just the initial algebra. And the reason that I'm doing that is what I'm about to say. So this is where we get the black box. Black box, which is some stuff about monads and transfinite constructions. Okay, so there's this thing called a monad. At this point, I'm going to assume that everybody knows what a monad is. Is that reasonable? And monad algebras. A monad has a notion of algebra, of monad algebra, which is not the same as an algebra for the underlying endofunctor of the monad. In this sense, it has some coherence conditions on this map algebra structure. But it's always true that the forgetful functor from the category of monad algebras for a monad always has a left adjoint. Right? So if T is a monad, then the category of T monad algebras, which I will write like this to distinguish it from endofunctor algebras, always has a left adjoint, which is essentially just given by applying T itself. And that gives you the free algebra. So when we're trying to build an initial algebra in endofunctor algebras, it would be enough to know that this is a monadic category, that there's some monad whose monad algebras are the same as endofunctor algebras for F. Right? So in a sense, what we're doing here with this left adjoint, which is a slight generalization of constructing the initial algebra, is we're building a monad whose category of monad algebras is equivalent to this category of endofunctor algebras. Right? So there's a theorem, which is our black box, which I don't actually know who originally proved this theorem, but the usual reference is this paper by Max Kelly. It might have been him who originally proved it, called Unified Treatment of Transfinite Constructions, et cetera, which is really terrible to read, but at least there's an NLab page which simplifies it a little bit. I don't remember. Anybody know? Maybe 1980?
78?
Maybe.
Because I feel we may have to look.
So I'm not, as I said, I'm not necessarily attributing the theorem to Kelly, but that's sort of the canonical reference to look for, which says that if F is an accessible endofunctor, of a locally presentable category. So remember, I assumed my model category was locally presentable. Then there exists a monad, F bar, such that the F bar monad algebras are equivalent to the F endofunctor algebras. And F bar is constructed in precisely this way. And so this is essentially an encapsulation of this theorem, that construction. And this F bar is called algebraically free. On F. It's called algebraically free because it's a slight strengthening of the idea of being freely generated by F in the sense of a left adjoint to the forgetful functor from monads to endofunctors. So there is a left adjoint to the functor, that forgetful functor of restricted to accessible thingummies, and this is in fact such a left adjoint, but this universal property is actually slightly stronger than that. although it's equivalent in the case of a locally presentable category. Okay, so essentially what we're doing here is we're building the algebraically free monad on an endofunctor. But now what I need is a little bit more than that. In order to deal with the case of higher paths and in a consistent way with the case of multiple constructors, I need something similar to this called an algebraic colimit of monads. So suppose we have a diagram of monads. So this is I have a bunch of monads and a bunch of monad transformations between them. And then I can consider having a cocone under this diagram. So this is a cocone in the category of monads on some fixed category, C. Okay. Then I can look at the categories of algebras for all of these things. So if I have a T monad algebra, then I can restrict that algebra structure along any of these maps, and that gives me a forgetful map into the monad algebras for any of these guys. T1 monad algebras, T2 monad algebras, and so on. And then I have a corresponding diagram here of categories over my category C. Okay, so we say that over here, T is an algebraic colimit of the diagram if the second diagram is a limit of categories. So what that means is that T is an algebraic colimit means that to give a T algebra structure on some object is equivalent to giving compatible algebra structures for all of these monads. That make sense? And then the really black box theorem, yes?
You need a C in that diagram. Everything is C. Over C, something like
Yeah. Yeah. Yeah, thanks. Is that good enough? Okay. Yeah, so it's not just a limit of categories, it's a limit of categories over C.
Yes. This is an example where you actually take a limit of categories and not absolute limit of categories.
Yes, but I don't think it's really essential because these are all isofibrant over C and probably.
Yeah. Shows that the notion of limits of categories is useful sometimes.
Yeah. That's a discussion for another day. So this is another theorem from which is in Kelly's huge paper, which is that if C is locally presentable and all the TIs are accessible, then algebraic colimits exist. So given the diagram, there is some monad T with a cocone with this property.
Again, accessible.
What? And again, accessible. And is accessible.
Is it for finitely many TI or for any collection?
Any small collection, any small diagram. Although we only need it for finitely many. Okay, so this is our black box. And now let me explain what this black box has to do with this case, and then we'll go on to higher paths. Okay, so in this case where we have multiple constructors, multiple endofunctors, one thing we could have done is consider algebra structures, an algebra structure for this pointwise colimit of endofunctors. But another way that we could have done it is we could have said, let's build separately the algebraically free monad on F1. Let's see. So, and then the algebraically free monad on F2 and take their monad coproduct. So to give an F1 endofunctor algebra structure is the same as to give an F1 bar monad algebra structure by the definition of being algebraically free monad, and the same over here. F2 bar of X monad algebra structure. And now the property of being a algebraic colimit means that this is the same as to give a monad algebra structure for the monad coproduct of F1 and F2 on X. Right, so I take the coproduct, the algebraic coproduct of F1 bar and F2 bar as monads, and then an algebra structure, monad algebra structure for that is the same as a monad algebra structure for F1 bar and for F2 bar, and those correspond to endofunctor algebras for F1 and F2. Yes?
All of a sudden, I have the impression I got lost much earlier. You said that you want to consider the endofunctors corresponding to each constructor.
Right.
And they are accessible.
Right.
So that means the endofunctor corresponding to S, which is the identity functor, is accessible.
Mm-hmm.
That doesn't correspond to what I thought about it.
Accessible means that it preserves sufficiently highly filtered colimits. So the identity functor preserves all colimits. So in particular, it preserves filtered ones. So this gives us a different way to construct the free joint algebra, joint endofunctor algebra for F1 and F2 by this monad coproduct. And of course, it's important that the coproduct of monads is different from their coproduct as functors. It's built by some sort of transfinite construction that throws in operations from both monads simultaneously and builds them off together off to infinity.
You're giving this example just to illustrate the notion.
Just to illustrate the algebraic colimits.
Somehow this is not very economical way.
Right.
Because you could
Right.
have done it in a much more simple way.
Right. So in fact,
Hopefully you're going to use the machinery for something
exactly.
you can't do in the more
So the monad coproduct of free monads is the same as the free monad on the endofunctor coproduct, right? Because free functors are left adjoints and preserve colimits. So this is the endofunctor coproduct, which is just pointwise, which we used up there. The sum, yeah. But now we're going to usually use it. Probably looks like I'm going to run over a bit. So let's consider a higher inductive type with one constructors, which is recursive. So yes? I'm avoiding vibrancy for the moment. Yeah. So we're not going to worry about whether our types are fibrant. We're going to deal with that again later. So for recursion, we have some inductive type, some higher inductive type, and it has some zero constructors, maybe several of them. And then I'm going to suppose, well, let's suppose it just has one constructor. Which gives us something which gives us a path from U to V, whatever U and V are. Okay? So what I'm going to do is I'm going to start by supposing that all of the zero constructors give me a monad. So we know how to deal with zero constructors. We did it right, like just up here. We could take the monad coproduct, or we just take the coproduct of all those endofunctors and build the free monad. And now I'm going to say, how do we add the one constructor? And what we're going to do is we're going to get a new monad. Maybe T hat or something, whose monad algebras are the algebras for the whole inductive type. And then the free algebra, the initial algebra for T hat will be our higher inductive type, modulo vibrancy. Okay? So how do we do that? Well, first of all, what are U and V? Okay? U and V are the most difficult part of the syntax of higher inductive types. The hard part is specifying what the syntax of U and V should be. They're expressions in type theory. They're terms which can involve these arguments, and they can also involve the previous constructors. So for example, in the case of S1, we have base, and then we have loop, which is a path from base to base. So here U and V are involving the previous constructors. But in the case of truncation, say the -1 truncation of a type A, we have a zero constructor that mapped from A into its -1 truncation. And then we have a constructor which says for all x and y in the -1 truncation, x equals y. So in this case, U and V are terms that involve things input from the arguments as well. So there's some terms of that sort, and there's some syntactic restriction on u and v in order to make this work. And what we need that syntax to give us is we need u and v to be natural transformations. From what to what? Well, from f to t. Everyone says, so f is the endofunctor corresponding to these arguments, and t is the monad we got from the previous constructors. And so my claim is that what we need is that u and v have to give us natural transformations from u to v, from f to t. So why does that make sense? F builds in the arguments of this constructor, and t already involves the previous constructors. So it's some term. So given a w, which is an algebra for the previous constructors, I can apply all of those constructors to it.
Intuitively, it's a relation that you're putting in.
Yeah.
Three algebra.
Yeah.
Among the operations of the three algebra.
That's a very good way to think about it, right?
Representation by generators and relation.
Right. Yeah. So u and v are like words in the theory specified by this monad, and we want to make them equal. So we want to take some sort of co-equalizer or something or other of these two maps, and f is telling us what the parameters are of the things that we're trying to identify.
But can the u and v involve also type theoretic operations like lambdas and pairing and
Yeah, I mean they can be complicated type theoretic terms, but they have to be natural to make these. I mean, so this is the hard part is specifying that naturality condition.
somehow be covariant?
Yeah.
So what would make them unnatural?
Get put up into an
Yeah.
exponent of variable.
Yeah. If I don't want to get into that because I'm out of time. If you have an arbitrary variable, like if I have, it has to be natural with respect to morphisms, not just isomorphisms. So if I have like any constructions that involve like contravariance and covariance, will mess up your covariant functoriality, and then you do constructions on those. It's not going to be natural in covariant functors.
So there's some kind of syntactic condition that would be
Yeah.
nice to specify.
Yeah.
For now.
Yeah.
Just a remark, in the case of polynomial functors, there is a notion of maps of polynomial functors, and the naturality is just a map between the actual
Mm-hmm.
descriptions of the polynomial. It's taken care by itself.
Right.
Naturality is automatic in the context of polynomial.
Right.
Can be.
But here we need to use the monad here rather than the polynomial functors that went into its arguments, because u and v might involve these constructors more than once. We could sort of apply one constructor to another constructor and another constructor, so it has to live in the whole words, right? Yeah. So an algebra for this whole thing should be a T-monad algebra, such that when we restrict that monad algebra along u and v to get maps out of f, then those maps are homotopic. So an algebra is an X together with a T-monad algebra structure, and together with a homotopy from fx, a homotopy between these two maps from fx to x. So we have something, and I can write that in adjoint form by taking fx plus fx maps to tx plus tx, and then to x. So this is this is u and v, and then this is the two algebra structures, and then this has to extend to fx times the simplicial interval. Okay, so this should look kind of familiar from what we were doing over here, right? So what I want is a monad. So this is a monad algebra structure. These are only sort of endofunctor algebra structures, but I can make them into monad algebra structures by taking the free monads on these things. Right? So this is the endofunctor coproduct of f and f, and this is something like f times delta 1 of x. I have two different endofunctors here, and if I build the free monads on these things, then this is a diagram of monad algebra structures. So I'm saying that given I have a monad algebra structure here, And then when we restrict to a monad algebra structure for this monad, it extends to a monad algebra structure for this monad
F is only given to you
as an endofunctor.
You have to
Boost it up
in order
to a monad in order to make to consider this as a diagram of functors. And so now what I need to do is I need to take some sort of monad colimit. So it's not exactly this because I need to build in the, right? So really what I want to do is factor through tx, right? So so this should, sorry, I'm getting kind of messy here. This should really be, to be analogous to this should really be factoring through the algebra structure on, the T-monad algebra structure on X. But then now if I take the monad coproduct here, whatever this is, I'll call this T hat. So this is a monad push-out, sorry. Then algebra structures for T hat will be the same as T algebra structures, which when restricted to F plus F extend to a homotopy between those two things. So then W, the
higher algebra.
yeah, T hat is the monad for all of the for the higher inductive type that adds in this new one constructor. And now we can do that again iteratively. So this is where we get to the point of what I said before, where what matters is the order of these constructors, because later constructors can refer to previous ones. But if I had another one constructor, then I get my monad T hat for these, including maybe a one constructor, and then I can add another one constructor by taking another monad push out to get a new monad whose initial algebra will be the higher inductive type for that. Okay. So the last thing to say is something about vibrancy, I guess, if you'll give me a minute or two. So all of that plus vibrancy. So here, yes.
As long as we're still
Yeah.
thinking about this.
Yeah, sure.
We could simplify the situation if we didn't have any recursion and we just had the higher paths. Then we could just work with the endofunctors. We wouldn't need to pass to the monads. Is that right? Well, if we have higher paths, we have
Yes.
recursion.
Yes, I agree. Yeah.
We
Yeah.
need the monad
In order to build in the recursion. Yeah. Which is sort of what we did with the circle over here, right?
Yeah.
We're just working with these constant endofunctors. Yeah. So for vibrancy, basically the idea is you take your monad T, and then we take a monad coproduct with a vibrant replacement monad. So the point is that there's a monad, an accessible monad, whose algebras are structured vibrations with chosen, like in the case of Kahn complexes, in the case of simplicial sets, the R algebras are maps with chosen lifts for all of your horns, chosen fillers for all of your horns. And now if we take a monad coproduct for both of these things, then it's going to be a T algebra and also an R algebra. So in particular, it's going to be a T algebra and also a vibrant object. And so the problem with building in vibrancy the way we did before is that if we just take a naive vibrant replacement, it's not necessarily going to be a T algebra anymore. The vibrant replacement doesn't preserve algebra structure for a monad. But on the other hand, if we took a vibrant object, T doesn't necessarily preserve vibrant objects. So we have to sort of put them together, and the monad coproduct gives us exactly the way to do that. So the existence of this monad R is again sort of a black box that Richard proved using a algebraic small object argument built on this sort of stuff. And then it turns out that from this we can extract the eliminator property, which I feel kind of bad about keeping you any longer, so maybe I won't actually describe how we do that.
So there is one point, what about preserving weak equivalences?
What about preserving weak equivalences?
Yeah, we would like somehow these monads to preserve weak equivalences or to respect something about the homotopy.
I don't think we need them to.
Really?
No?
Probably prove that.
You can probably prove that they, I mean, yeah, you can probably prove that they do in the type theory. Once you've got the type theory, you could prove that the construction, everything respects.
You're doing it in a model category theory.
Yeah.
I think that they do not in general in a model category.
Yeah, certainly. I mean, just arbitrary things won't in general. I don't know. Fortunately, we don't need it to build the model of the type theory, so I didn't worry about it.
Because in type theory, everything you say the philosophy will preserve.
Right. So once we can say it in type theory, once we can deduce the type theoretic property, then everything will be invariant.
No, but this monad as a functor doesn't actually figure in the construction all that much. It's only its initial algebra, or it's basically only its initial algebra which enters. It's not it's only at the end. It's only applied to the empty type, and roughly speaking. Right?
Yeah. Yeah.
You can equivalently recover the values of the whole functor though by just throwing in extra zero constructors
Right.
corresponding to any type. So I mean you can essentially recover the rest of the monad as well, or
Yeah.
its action on objects.
Yeah.
You take all the elements of a set as
No, I
constant.
mean this construction has to preserve weak equivalences between these functors like f. So if I replace f by f prime, where f prime is weakly equivalent to f, then the result should be weakly equivalent. So it's not like the monad should preserve weak equivalences, but this construction should preserve weak equivalences between monads. Something like that.
I think it also does preserve equivalences between fibrant objects, at least, because like Peter said, you can see the whole monad by adding an extra zero constructor that takes a parameter. So if I threw in x as a parameter and then I have another zero constructor which says x maps to w, then the inductive type with these constructors will be the free thing on x, and so it's going to preserve those equivalences. Yeah.
The type theory itself has a model structure,
Mm-hmm.
as we learned last week or 2 weeks ago, and it doesn't satisfy these conditions, right? But if it has assume higher inductive types, it would be kind of nice if the semantics would specialize to that case to give us a description of what's going on there. And only some of this theory is going to work because of the colimits.
Yeah. Yeah.
Just a comment. Just saying.
I mean, all this is somehow analogous to Vladimir's construction of the universe of con-complexes using particulars of simplicial sets or model category theory, minimal vibrations.
Right.
It's sort of at that level,
Yeah. Fair.
which, I mean, isn't to say that it wouldn't be nice to have a better understanding, but it at least gives us as good of an understanding of higher inductive types as we have of the rest of type theory in model categories.
If you only have ordinary inductive types, this means only zero constructors, you can describe them as initial algebras for polynomial functors.
Mm-hmm.
So do you know what kind of class of functors do you get by adding, say, one constructors and performing this machinery? No?
I don't know any property that they all have other than being accessible. That's a good question.
You know, we know a conjectural answer that if you add all levels of constructors, then you recover all accessible functions. And then there should be a notion of, and polynomial functors kind of are free accessible functors, and then the functors with one constructor are polynomial plus one level of relations on them, two constructor polynomial plus three level of relations, and two level of relations, and then all accessible ones are presumably polynomial plus infinitely many levels of relations. That's what came up from Monday discussion. After you have installed. But that's some kind of somewhere in the sky. I don't know.
Richard?
So I'm slightly puzzled by this last step.
Yeah. So what you need is the elimination property. And that rather than extending along that map, what we use instead is the fact that our algebras compose. So if I have anybody who wants to leave can feel free. So if R is if W is the initial T prime algebra, and I have a fibration. So this is a fibration which is a T algebra map. So it's a fibration, so I can choose an R algebra structure on it. Right? So that means that, right, so I can choose an R algebra structure on it. Now, R algebras compose, so P to W to 1 gets an R algebra structure. With the property, moreover, that this is also an R algebra map. Therefore, it's a T prime algebra map. But W is the initial T prime algebra, so it has a section, which is a T prime algebra section. Yes?
Just a comment on Nicholas' remark. I didn't understand your answer, but or your conjecture. But I mean, it's clear that we get some functors, some new functors, like where the type of shapes is a group of these. So we get, for example, the multisets, which are not usually polynomial functors.
Which set?
The functor, the multiset functor, the functor which given a set, considers the multiset, so the lists where you can commute the order arbitrarily.
The free commutative monoid
Yes,
on
exactly.
the set.
Mm-hmm.
Yeah, right. So it will give you all kind of algebraic theories with relations,
Yes.
high relations.
Yeah, that's
Mhm.
okay.
Yeah, that's
Yeah.
what I meant. Yeah. And like relations between relations, because it's up to homotopes and stuff like that.
So this is like corresponds to analytic functors. I mean, it's a general
That
notion
corresponds
of
to.
polynomial functors where you can
No, I don't think so.
more general.
It's
It's
much
usually-
more general. It's much more general.
yeah, it's more general, but
You would get
Yeah,
those.
I think you should get all accessible functors in there.
You should, you,
I mean,
may-
that's a bit of a stretch.
maybe all internally accessible functors, because they have to be presented by internal things.
I mean, the usual polynomial functors preserve pullbacks, right? And these don't preserve pullbacks.
Right.
So there is a weaker condition. Yeah.
Possibly going in your question, these are more general than those polynomial functors using group loads, in that if we just looked at cases where the terms u and v were themselves zero constructors and no more than that, then we would get something like polynomial functors for group loads, because it's saying each of the paths we're adding, each of the one constructors goes between a pair of zero constructors. But here we want in general to have cases where u and v are not just those zero constructors, but they can be built out of those using lots of Adjoint operations and so on. And so the one constructors don't just go between zero constructors, they go between more general things.
So there's a nice
Can't describe a shape just as a group load.
so there's a nice example that Peter showed me a while ago of you can build the free type together with an involution. So where I have one constructor that goes from W to W and another constructor that says for all x, f of x is equal to x. So you can this is an example where you can iterate the zero constructors in U and V.
It seems that since all the algebra are algebra of the monad, in fact, what you're doing constructing algebraic theories of general algebraic theories, unisorder algebraic theories.
Mm-hmm.
So in this sense, what you can construct here is all about essentially, more generally, one may say essentially algebraic theories, models of essentially algebraic theories.
Mm-hmm.
Do you know that?
Um,
One
yeah.
could do that with the theory of sketches.
Right. Yeah. We
So
this was brought up before. Yeah.
there is another approach to
Mhm.
that, with the theory of sketches.
Mm-hmm.
I mean, I guess all these monads you build are vibrant.
In some sense, yeah. Yeah.
Okay, so then it's your general theory of sketches.
Mm-hmm.
When you get indices, I don't know what you get when you get indices.
I think people would like to go to lunch.
Parameters are indices. When you get parameters, you can get multiplicative theory.
Right.
When you get also indices,
Yeah. Why don't we let people go to lunch, and then those of us who are interested can finish. Thanks.
People were more interested in this than in lunch.